We're going to focus on a combination of lessons. It's a little bit of 5.4 and a little bit of 5.5. So what we have to understand and remember is what the sine and the cosine function look like. So a little bit further down in the notes, there's two functions. One is blue and one is red. It's kind of hard to see with the font that I put there. So I'm right here on the side. This here is going to be the sine of x. So if you can recall, the sine of x starts at 0, 0, goes up, and then comes back down and repeats. And the blue one's going to be the cos of x. So if we're looking at a range of values for the sine and the cosine function, the lowest value that it can be, unless there's an a value that stretches it, is going to be -1, and the highest value, unless there's an a value that stretches it, is going to be 1. And then the properties of the sine function, if I were to take the sine of an x and add 2 pi to it, it would actually bring it back to the exact same y value. So we say that sine of x plus 2 pi is equivalent to saying sine of x. And you can read over those properties on the way down. For example number 1, it says compute the following limits. So it says the limit as sine of x, limit of sine of x as x approaches infinity. It says from the graph, so I want to scroll down a little bit. And what we have is a problem because the value for sine of x consistently changes as the x value changes. So it does not approach a finite number. So we're going to say that the limit does not exist. Same thing would happen is if we took the limit as x approaches negative infinity of the sine of x. We would say that the limit does not exist, and explain already why for the positive side. For example number 2, it says use technology to evaluate each limit. So I'm going to go about this a slightly different way. I'm going to do it as a one-sided limit. I'm going to say that this is equivalent to saying the sine of x, and x is going to be a really small number. I'm going to pick 0.001, and I'm going to put that over 0.001. That's for x. And if we put that into our calculator, we're going to get a number that looks something like 0.123, 1, 2, 3, 1, 2, 3, 3 nines, and then 8, 3 repeating. So if we think about that logically, that is a number that's pretty close to 1. So I'm going to say that therefore the limit as x approaches 0 of sine of x over x is going to be equal to just 1. I'm going to use that same type of method to actually solve for the cos function that we have for part B. Excuse me. So what I'm going to do is I'm going to say that we're going to take the cos of a value very close to 0, which would be 0.001 minus the 1 at the end there. And remember, that's the -1 that's separate from the cos function, and that's all over 0.001. When I put that into my calculator, I get something that looks like negative 0.0005, I believe. And therefore, we conclude that when we take the limit as x approaches 0 of the function, that it's approaching 0. So it's going to be equal to 0. Now, the great thing about calculus is that basically when you're taking derivatives, it's a bunch of patterns and formulas that to memorize, right? So all we really have to memorize is the derivative of sine is going to be equal to cos. You can go ahead and read the proof. It's pretty self-explanatory. I haven't really finished it, so let's look at it together, I guess. If we're taking the derivative of sine, and we go back to first principles, really what we're going to do is take the limit as h approaches 0 of sine of x plus h minus sine of x all over h. And what I'm going to do in this case here is expand the sine of x plus h, and we're going to simplify. So the sine right? The sine in the first part is actually constant, so I can take it out. And the cos over here is a constant, so I could take it out. So we can focus on taking limits on the second half. So what I have to do now, it says now use the answers from example 2 to complete. So therefore what's going to happen is we're going to say that the sine of x, its derivative, is equal to the sine of x, and then the limit, we can actually see the limit here is part b from above, so it's going to be times 0, plus we're going to have the cos of x, which is our constant, times our value, which we said was going to be 1 from above, part a, and that's going to be it, all right, because it's already taken care of. Now, we know that anything multiplied by 0 is be 0, so that all cancels out. The 1 has no impact on the calculation, so therefore we can say that the sine of x derivative is basically equal to the cos of x, which is kind of what we said the formula was. The next few formulas that we need to know is if I take the derivative of sine and inside the bracket there's a function, okay, basically the derivative of it is going to be the same as what we had above, but we also have to take the derivative of what the function is. Next formula we have to know is the cos function. Taking derivative of the cos function will give us a negative sine function. Again, there's the proof, you can look it over for yourself. And then we have derivative of tan. So derivative of tan is basically this part right here, all right? But we know that 1 over cos squared of x is really the secant squared of x. And the same premise goes for the function. When we have actually a function inside the bracket, we have to take derivative of the function as well. And again, there's a proof for you to look over at your leisure. Let's try some examples. So the first one says differentiate. Just so we're on the same page, remember there's two parts of the function here. There's x to the exponent 3 and there's the sine of x. So we have to use a little bit of the chain rule, a little bit of the product rule. There's a bit of everything going on here, right? So if I want to take derivative, I'm going to take the derivative of the first part of the function. So the derivative of x to the exponent 3 is 3x squared times the sine of x. And I'm using the product, so it's going to be x to the exponent 3 times the derivative of sine, which is going to be the cos of x. And we always try and simplify as much as possible, so in case we have to use a different calculation, I can see that I can factor out an x squared. And I think that's pretty much it. So if I do that, I have x squared. And what's left is we have the 3 from in front of the x squared, sine of x, plus we have an x left, and we have the cos of x. And if I try and simplify the bracket further, I can't see anything that comes to mind, so we're kind of done. For example B, we have to remember that derivative of e to the x is e to the x times derivative of the function. Well, in this case here it's x. All right, so we're using the quotient rule. So derivative of the numerator is going to be e to the x times 1 over times the denominator minus, and I think I wrote that too big, so I'm going to delete that and start again. Let's try that again. So derivative of the numerator is e to the x. I'm not going to put the 1 because it's going to take up space, times the sine of x, the denominator, subtract e to the x, the numerator, times sine, derivative of sine, which is cos of x. And that's all over the denominator squared. So the sine of x all squared. We always try and simplify as much as possible. I can take out an e. So if I take out an e to the x, what we have is the sine of x minus the cos of x all over sine squared of x. And we can simplify a little bit more. I'm not sure if it's going to be of big value for us, but we have e to the x times 1 over the sine of x. Subtract the cos of x over the sine squared of x. So I think the second one is a little bit better than the last one. And we have one more. We have the ln of sine of x. So remember the ln function, when we take the derivative of ln, it's 1 over the function itself. So when we take the derivative of ln of sine of x, it's going to be 1 over the sine of x. But then we have to take the derivative of the function itself, so the derivative of sine is going to be the cos of x. If we simplify this, really what we have is the cos of x over the sine of x. And really, if we think about this, it's the same thing saying the cotangent of x. So we're going to start example number 4. And before we do that, I'm just going to put a note at the top of the page that we can refer to. I just want you guys to note that the sine of x squared is equal to the sine squared of x, but does not equal the sine of x squared. And we'll see that further down in our calculation. So let's try the next one. Excuse me. So our derivative of a is going to be derivative of the first part of the product, which is going to be 1, times the second part of the product, sine of x. And it's a product rule, so there it is. And then it's going to be the first times derivative of the second, so it's going to be cos of x. We always look for ways of cleaning this up. Really, there's nothing for us to clean up, so I'm just going to rewrite it as sine of x plus x cos of x. Excuse me. The next one we have the tan of x, so our derivative, before I do that, let's do tan of x equal to the sine of x over the cos of x. Let's say, for example, we forgot what the formula is on a test, all right? So we can actually do it from first principles. So what we have now is the derivative is equal to the derivative of the numerator, which is going to be cos of x times the denominator, cos of x. Subtract sine of x numerator times derivative of cos of x, which is negative sine of x. And that's going to be all over the denominator, all squared. We can simplify this a little bit. So what we have here is cos squared of x. The two negatives, negative sine of x times negative sine of x, will be plus sine squared of x all over our cos squared of x. And we should hopefully remember the property where we have sine squared plus cos squared, that's equal to 1. So we have 1 over the cos squared of x, which in this case here, y prime is going to be equal to secant squared of x, which is one of the formulas we had to memorize. I'm going to move that over just a little bit, just so we have a little more room. Okay, let's try the last one. So for the last one, remember this here is our f of x. So when I take the derivative of cos, we know it's going to be negative sine, and we still have our x squared minus our 3x plus 5. And then we also have to multiply by the derivative of the function f of x. So I ran out of space there, so I'm going to put it down below. So it's going to be 2x minus 3. So when we clean this up, we're going to get therefore y prime is equal to, we always want the value inside, or the term inside the bracket, to be starting with a positive. So it is start with a positive. So I'm going to leave the negative outside. So we have our 2x minus 3 times our sine of x squared minus 3x plus 5. Sorry for squishing it in there. For example D, once again, I'm going to use some kind of little shortcut or something to help my brain out in case I can't remember the formulas. We know this is the same thing as saying sine of x times the sine of x. So now I can use a product rule. So if I want to find the derivative of h, then we know it's going to be derivative of the first term, which is going to be basically cos of x, times the second term, sine of x, plus sine of x, which is the first term, times the derivative of sine of x, which is cos of x. And we can see that this repeats. So we can actually say that this is equal to 2 times, I'm going to put the sine of x, cos of x first. That's the way we usually do sine first. And if you can recall from advanced functions, this is really the same thing as saying sine of 2x, which is our double angle. That's horrible. So remember that note we did at the top? Let's move it down so we can see. Yeah, it's going to apply now, right? So notice that we have the very end, so this is not equal to sine squared of x. So we got to be careful with this one, right? So we know that p prime of x is equal to derivative of sine, which is going to be the cos. So it's going to be really the cos of x squared times the derivative of the function, which the function in this case here is x squared. So it's going to be times 2x. And if we clean it up, we're going to have 2x cos of x squared. Try another one. So in this case here, it looks like it's going to be the product rule again. So our derivative is going to be derivative of e to the x, which is e to the x, times derivative of x, which is 1, which I'm not going to show, times the cos of x, plus e to the x times derivative of cos of x, which is negative sine of x, times derivative of x, which is 1, so I'm not going to show. And again, we always try and clean this up as much as possible. So y prime is going to be equal to, I can factor out an e to the x, and what I have left is cos of x minus the sine of x. And I really can't do anything with the bracket, so we're done. Example G. So I don't have this as an equation, so I'm just going to put f of x, right? So if you want, you can call that f of x just to make it easier. You can do that for all of them. So when we do f prime of x, it's going to be derivative of x to the exponent 3, which is 3x squared, times tan of x, plus x to the exponent 3 times derivative of tan, which hopefully we commit to memory. If we didn't commit that to memory, then we had to convert tan to sine over cos, and they'll take a little bit longer, right? So in this case here, it's going to be times secant squared of x. I'm going to see how I can clean this up. We always like seeing answers with coses and sines. So if we do that, just write it out. We're going to have 3x squared times sine of x over the cos of x plus x to the exponent 3. Excuse me. Fix the 3 out. Over the cos squared of x. We can pretty much factor out an x squared, and we can factor out, if you want, a cos squared, or we can, let's see what this looks like. This is only one possible answer. There's going to be multiple, right? So I know I can factor an x squared from both of them. And if I leave like that, all right, what's left? We have the 3, and we have the sine of x. And I'll leave a little bit of space, and I'll explain why I'm leaving the space in a few seconds. If I want to make the denominator cos of x, that's not a problem, but I can't. Can I do that? I can. If I want to keep it as one denominator, basically what's going to look like is this. All right. So instead of having it split, I can actually make the denominator cos squared of x. That means I need to multiply this by cos of x plus x. The reason I put the answer like that is I can now change that cos squared of x, if we're continuing another calculation, to 1 minus sine squared of x, and hopefully something will cancel out. So multiple ways to represent that answer. I think I'm going to have to start writing smaller, so I'm going to zoom in a little bit. So for cotan of x, basically that's the same thing as saying 1 over tan of x, which is the same thing as saying cos of x over the sine of x. Again, if you can't remember the formula, you can go back to first principles. And if I take its derivative, it's going to be derivative of the numerator, which is going to be negative sine of x, times the denominator, sine of x, minus the numerator, cos of x, times derivative of the denominator, which is going to be cos of x, all over the denominator squared. If we clean this all up, I'm going to factor out a negative, and we can see that this here is really sine squared of x. This here really is cos squared of x. If I factor out a negative, we have f prime of x is equal to negative sine squared of x plus cos squared of x all over the sine squared of x. And we know that this now is one of the identities, equals to 1. So if we clean this up, we have negative 1 over the sine squared of x, or our final answer, if you want to write it in a different form, will be negative cosecant squared of x. I'm going to have to write small for this one. When I want to take the derivative of tan, we know that the final answer is going to be 1 over, so we know that derivative of tan is equal to 1 over cos squared, right? So I can use that information. Lots of ways of doing this, but I'm going to use that one there. So when I take the derivative of tan, we're going to have our 1 over the cos of the function. Then I have to take the derivative of the function. So really the function is the same thing as saying we have the tan of x squared plus 1 to the power of 1/2. So it means I'm going to drop the 1/2. And we know when we drop the 1/2, we're going to subtract 1, it's going to give us a root on the bottom. Then I have to take the derivative of what's inside the radicand. So in this case, it's going to be times 2x. The 2's cancel out. We have f prime of x. The only thing that's on the numerator now is x. Now the denominator, I'm going to bring the root to the front. So we're going to have the root of x squared plus 1 times the cos of x squared plus 1. So for the next one, we're finding the equation of the tangent to the graph of y is equal to x cos of 2x at a certain point. So what I'm going to do is I'm going to take that x and plug it in to find out what my y value is. So y is equal to pi over 2 cos of 2 times pi over 2. The 2's cancel each other out. So now we have cos of pi. So cos of pi for cos function, remember it looks like this, where this is going to be 2 pi. And this here is going to be pi. So we know that cos of pi is negative 1. So that means it's going to be pi over 2. Therefore, our point is going to be pi over 2, negative pi over 2. We're going to need that later on. So just calculate it just right now. I could have done it later on. And in order for us to take the derivative of the y function, what I'm going to do is still call it y and call it f of x. So it's just a little bit easier, right? And now I can take my derivative. So we're going to have f prime of x is equal to the derivative of x, which is 1, times the cos of 2x, plus our x times derivative of cos of 2x, which is negative sine of 2x, times I got to take derivative of 2x, which is 2. When I clean this all up, I have our cos of 2x, 2 times x times negative minus 2x sine of 2x. And now I can plug in the value to see what the slope is going to be, right? We know we want to find the slope at pi over 2. So when I do that, we're going to get the cos of 2 times pi over 2 minus 2 times pi over 2 sine of 2 times pi over 2. Sorry for going into the graph. And we can do some simplification, right? Really, this is the same thing as having a bracket around there, so that I can cancel out the 2's there. I can cancel out those 2's there. I cancel out those 2's there. And I didn't label this here. This is a cos function, right? If I were to do a sine function, it's going to look something like this, where this is pi, this is going to be 2 pi. It's sine, right? And we have cos of pi, which is going to be negative 1. So we have f prime of pi over 2, which is equal to negative 1. And then on this side here, we have pi times sine of pi. Sine of pi is 0. So we know that this is all going to 0. That means that it's just negative 1. Maybe I should write it all for you guys, make it a little cleaner. Yeah, I'll write it out, just make it a little bit cleaner. So what we're going to have here is really the cos of pi minus pi sine of pi. So we know that f prime of pi over 2 is equal to negative 1. So the next thing we got to do is find out the equation of that tangent line. So I'm going to use y is equal to mx plus b. We could have used the other form as well, but this one I think is a little bit easier. So we know our slope is negative 1. So we have y is equal to negative 1x plus b. And I got to plug in a point. I know for sure it's on the line. So that's that red point we calculated at the very beginning. So I'm going to plug in pi over 2 and negative pi over 2. So we have negative pi over 2 is equal to negative pi over 2 plus b. When I bring the pi over 2, negative pi over 2 to the left, we're going to have b is equal to 0. So therefore, we can say that our equation is y is equal to negative x. For the next example, it's asking us to find the points of inflection. So when I ask for points of inflection, we know we have to do a double derivative. So before I start, I'm going to pretend I don't know what the formula is, which is not hard, cos squared of x. And I'm going to say that f of x equal to cos of x times the cos of x. So when I do its derivative now, I'm going to take the derivative of the first part, which is going to be sine of x, negative sine of x times cos of x. Plus we have the cos of x times negative sine of x. Or we can simplify this to be, we have negative 2 sine of x times cos of x, which, if we recall from advanced functions, it's the same thing as saying negative sine of 2x. The next thing I'm going to do is I'm going to take its double derivative. And the negative is really a constant. Derivative of sine is really cos. So we have cos of 2x, right? And maybe I should put that in brackets, times derivative of 2x, which is 2. So when I clean this up, we get negative 2 cos of 2x. And our goal is to make this equal to 0. So that's going to happen. I can divide both sides out by negative 2. So we're going to have cos of 2x is equal to 0. So remember, this is cos of 2x. So it means if I were to take its inverse, we can actually find out what it's going to look like. So I'm going to provide with a little sketch. So the cos function looks something like this. It's not really to scale. And because it's cos of 2x, that means this here is going to be pi over 2. And this here is going to be 3 pi over 2. So when we're solving for x is going to be equal to, in this case here, it's double that, so it's going to be pi over 4. Or we're going to have 3 pi over 4. And that's the only two values because we're restricted in its domain. So all we have to do is find out where the POIs are. So in our points of inflection are, well, we know it's going to be pi over 4. And when I plug it back into the function, pi over 4 squared, plug it in, we're going to get 1/2. And the second one is going to be when we have 3/4 pi, and well, it's be the same thing because they're on the same part of the curve. For example 6, an object suspended from an end of a string, so that probably means it's bouncing back up and down, whatever the case is. Its displacement for equilibrium position is given by the s function, calculate velocity and acceleration of the object. All right, so what I'm going to do is calculate the velocity, and we know that s prime of t will give us the velocity. 8 is treated as, I treat 8 as a constant. So if I take derivative of sine of x, we know it's going to be cos of x, but it's not x, we're talking about 10 pi t. Then I take derivative of 10 pi t, so it's going to be times 10 pi. Notice that the cos, I put brackets around what's in front of the cos, so that we know what's a number in front of the cos or after cos being multiplied. So I'm going to take the 10 pi and multiply with the 8, so we have 80 pi cos of 10 pi t. For acceleration, that's going to be my derivative of the velocity, which is equal to my acceleration. And same concept, I'm going to take my 80 pi, treat it as a constant. Our derivative of cos would be negative sine of the function times derivative of the function. So 10 pi again. And once again, I'm going to multiply the 10 pi with the 80 pi, and we get 800 pi. I'm also going to take that negative out, and we're left with sine of 10. Well, I don't need the bracket, so let's take the bracket out. Sine of 10 pi t. So we did our first second derivative for velocity and acceleration. Next thing we have to do is prove it. So here's my proof. So it says that we have the second derivative with respect to t. So my second derivative with respect to t is equal to negative 800 pi squared sine of 10 pi t. And then it says plus 100 pi 100 pi squared s. S in this case here was 8 sine of 10 pi t. And we got to see if this is equal to 0. So here we go. So that's equal to, well, if I multiply the 8 with the 100, we can see that there's opposite signs. So we have, that's going to be an opposite sign. We're going to have 800, and everything else is going to repeat. So when I do that, what's going to end up happening is, I'll just write it out. So we're going to have negative 800 pi squared sine of 10 pi t plus 800 pi squared sine of 10 pi t. And those are going to cancel out because they're opposite one another. Okay, let's do example number 7. A particle moves along a line so that at time t, which is measured in seconds, its position in meters is given by the function s of t, which is equal to 4 cos of 2t. Part A says differentiate the function with respect to t. So let's do that. So we're going to do s prime of t, which is equal to 4 as a constant, so I'm leaving that out. The derivative of cos of t is going to be negative sine of 2t. And then we have to multiply that by a derivative of the 2t, which is 2. We can simplify this. So s prime of t is equal to, well, I'm going to bring that 2 at the very end from the derivative of 2t to the front, and the negative as well. So we're going to get negative 8 sine of 2t. Excuse me. We know that s prime of t is really the v of t, which is equal to negative 8 sine of 2t. For part B, it's asking when is the first time that the particle changed direction. So the particle changes direction, so it changes direction when s prime of t, which is equal to v of t, is equal to 0. So I set that equal to 0. We have negative 8 sine of 2t. I'm going to divide both sides by negative 8, so the negative 8 disappears. So we have 0 is equal to sine of 2t. And you got to remember that 2t means you have the sine function which is being compressed, right? So in this case here, if I were to take the sine inverse of both sides, I'm still going to get 0 on this side, and on this side I'm going to get 2t. So we have to figure out when t is equal to 0. I'll just clean that up. And that happens when, well, t is equal to 0. And if I were to look at the s of t function, excuse me, if I were to actually draw the sine function, and this here is, let me label this as pi, 6 point, here is going to be 2 pi, so that's going to be pi up there. That's going to be 2 pi, so that's pi, 2 pi. This is going to be pi over 2. This is going to be 3 pi over 2. I forgot to mention that this graph here is really the sine of 2t. So we can see that it's equal to 0 right over here. All right, when it changes direction, pi over 2. When it changes direction up here, which is going to be pi. Changes direction down here, which is 3 pi over 2. But it's asking for the first time. So therefore, we're not going to count 0, so we're going to count the first time, which is equal to pi over 2, the particle change directions. All right, so part C says, when does the particle reach a max velocity for the interval of 0 to 2 pi? So we have to take its derivative again because we want so the max velocity, I'm going to write over here because I'm going to draw a little sketch. So the max velocity I'm not sure why it keeps on doing that, is at a of t is equal to 0, or v prime of t is equal to 0. So it means I take the derivative of my velocity. So my v prime is equal to, well, the negative 8 is a constant. Derivative of sine of 2t is cos of 2t times derivative of 2t, which is 2. So we can clean this up. It will be negative 16 cos of 2t, which happens to also be my a of t. And we said that v prime of t has to be equal to 0, and that happens when we have 0 is equal to, I'm going to divide both sides by negative 16, so we're going to have cos of 2t. So if I were to draw a little sketch of a regular cos function, a regular cos function would look something like this. So it starts up there, we're going to do 1, 2, 3, so it's going to go to here, down to here, back up. So that'll be the regular cos function I missed, but we know what that means. So that would be pi, that would be 2 pi, that's going to be pi over 2. We care about the first one, so I'm not going to label anything else. We don't have to. And for the function that we care about, it's going to be half of that. So that point will be somewhere down there, that point will be somewhere down there, that point will be somewhere up here, and then that will be up there. So we care about the first time. That will be the cos of 2t, right? And that's equal to 0 right there. And this will be pi over 4. So I have to label the rest. So it's pi over 4. The next one's going to be 2 pi over 4. This one here is going to be 3 pi over 4. That's 4 pi over 4. It's kind of hard to see, which is really just pi. In between here, there's going to be another point, which goes down, another point which goes down, a point which goes up, and then goes back up. So we have 4 pi over 4. This part is 5 pi over 4. This is 6 pi over 4. 7 pi over 4. And 8 pi over 4. So we want to find out when it's equal to 0. It's equal to 0 there, 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 and there. That means t will be equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Part D asks, what's the maximum velocity of the particle? So let's go back to our v of t. So maximum velocity, so we need the v of t, which is equal to negative 8 sine of 2t. I'm going to replace the t with my pi over 4, because they're going to be all the same. That means we have negative 8 sine of 2 times pi over 4, which is really 1/2. So this all goes to pi over 2, which is going to be equal to 1. And then we have v pi over 4 is going to be equal to negative 8. So the negative is this direction. Therefore, the 8 meters per second is the maximum velocity. It's a line of lines, so it's going to be left or right. So if I'm assuming right is positive, it's going to go back. Verify our answers by looking at the graph, and just by looking at my graph, I realized that I labeled this wrong. So incorrectly, sorry. This graph actually is 4 cos of 2t. So we can verify that information now with that part there. So that's going to be our pi over 4, and so on and so forth. And for the second graph, it's going to be our negative 8 sine of 2t. And again, we can go back and verify our answers using the graph as well.